I am not able to give the quiz one exam,
Oh,
and
okay.
now I am giving quiz two.
Okay. Okay. I have started the streaming and we are live now. And I have also pinned the YouTube link in the chat. Let me also paste it in the calendar. All right. Hope my screen is visible to all of you. And let's begin. So, in the last session, we were talking about series and how they are generated from the sequences. And then we have seen some very well known series, which are geometric series and harmonic series, and 1 by n power q series also. And we talked about convergence and divergence of those series. And then we talked about comparison test, right? So using comparison test, we can also comment on convergence of some other series, comparing them with very well known series like geometric series or uh, the harmonic series. Okay. And at last, we talked about the connection between the sequence and its generated series. So what is the connection between these two? Can we say something? So it turned out that if the series converges, right? So if this happens, this is statement A for us, okay, which says series converges implies sequence tends to 0. So this is statement B. So if A happens, then B will happen. And the same contrapositive statement of this is like if not B, then definitely not A. Okay, you can also imply that. So what does it mean? The same statement can be rewritten like this. If sequence does not tend to 0, does not. So if this is statement B and this is negation of B or not B, complement of B. If sequence does not tend to 0, then what happens? Not A will happen. Not A is like negation or opposite statement of A. What is opposite statement of A? Series diverges. Okay, so both statements are the same. So this is called math logic in some sense. So first one is statement A. Second one is contrapositive statement of the statement, given statement. So this holds true even if you see in real life examples, something like if it is raining, then the road is wet. Okay, so you can think of it like that. Then it is same as if the road is not wet, then it is not raining, right? So both are true in some sense. And in our example, like as we are all students, if you study hard, then you will pass the exam. If you do not pass the exam, then what does it imply? You did not study hard, right? And if you are working employee, you might think of it like if you have a job, then you get a paycheck. That means if you do not get a paycheck, that implies that you are not working. So something like that. So if A implies B is same as saying if not B or opposite of B, then opposite of A will happen. Okay, so this is important. This we are going to take now. If sequence does not tend to 0, you can straight away claim that your series will diverge. And that's the very first check we do. Whenever a series given to us, and if you want to comment on the convergence and divergence, before using any test, what we do is we check whether its corresponding sequence and its limit is tending to 0 or not. Okay. So first check will be that. Then after that, we will use different tests. So yeah, any doubt? All right. Okay. And this is also important. And sometimes we fall into wrong steps. If the sequence limit going to 0 it will necessarily not imply that it will converge, series will converge. And the best example is sequence 1 by n, harmonic series. So 1 by n sequence will go to 0, but summation 1 by n series will diverge. And the proof for this we have seen in the previous live session. So if you are interested, go back to that live session and look at the proof. And even in one of the lectures, professor has proved it. Okay. So that is one thing. Now what we will talk about next is, we will talk about two new tests which are called root test and the ratio test. Okay. So we have a series now. Yeah, any doubt?
Sir, we are continuing weeks or what?
Week 7, right? We are continuing.
Okay.
Yeah. So today's discussion is on week 7. Okay. And the deadline for week 7 graded assignment is on coming Wednesday. All right.
Sir, I
So,
think tomorrow,
sorry,
deadline of assignment.
deadline of assignment is tomorrow. Can you cross check? It's on 5th March, no? It is on 5th March.
Yes, sir. It is on 5th March.
Yeah, yeah. All right. So let's talk about some tests which are used to check whether a given series is convergent or divergent. Okay, so we have a sequence now, AN, and we have generated a series from the sequence, right? So this is the series and this is the sequence. And now we are trying to comment on convergence of the series, of this series. And how are we going to do? We are going to use these tests, very well known tests. And what does the test says? The root test actually talks about, takes the sequence first. So it takes the sequence and computes this limit. Okay, what is that limit? It is the limit n tends to infinite. What happens to, you take the nth term, absolute value of the nth term, to the power 1 by n. Okay. If it exists, okay, if it exists and it is equals to capital L, then you check this. Your capital L is less than 1, then your series will converge. If your capital L is greater than 1, then your series will diverge. If your capital L is equals to 1, then we are unlucky. We can't say whether the series will converge or diverge. We will say that root test failed. Or in other words, we will say that no conclusive result can be obtained. Okay. So that is root test. For root test, you have to compute this limit. And this limit should exist first of all. Okay. And then after you compute the limit, if it is less than 1, you claim that it is convergent, series converges. If it is greater than 1, you claim that it is diverges. Is equals to 1, we can't do anything. Okay. So that is root test. The ratio test is slightly easier. Okay. So instead of computing this very complex looking expression, power 1 by n something, what we do is we take the n plus 1th term, we take the nth term and its ratio. So from the word itself, you can see it's ratio between the n plus 1th term and nth term, and tend n to infinite. Okay. And if both of them exist, the fact or the theorem says that both the limits are the same. They will go to the same value. Okay. So instead of computing this limit, we compute this limit, and the following conclusion statement stays the same. So if this limit is less than 1, then we say series converges. If this limit is greater than 1, then we say it will diverge. If this limit is actually equals to 1, then we say again we have no luck, and we'll claim that, we'll state that there is no conclusive result obtained by using the ratio test. And sometimes there are series which may fail the ratio test, but it may pass the root test. Okay, so that is why we have to fix an order, or you should follow a flow chart, a series of steps to conclude whether a given series is divergent or convergent. And that is basically like this. So you can follow this particular flow chart. So the first and foremost thing you should check is whether the sequence limit is going to 0 or not. Okay. If it is not going, if no, if sequence itself is not tending to 0, then you can imply that your series will diverge. Done. For suppose if it is tending to 0, then the first test you have to use is the ratio test. Take the n plus 1th term, divide it by nth term, and then take the absolute value and tend n to infinite. If this ratio test works, that means if you can get that limit value either less than 1 or greater than 1, then you can conclude whether it is converges or diverges. If the ratio test giving you L equals to 1, or if L is giving you two different values, like limit is not existing, okay, then what we do is we move from ratio test to root test, and we will use root test. Again, use the root test. What is root test? Root test is computing the limit n tends to infinite, absolute value of an power 1 by n. What is ratio test? You have to compute this limit n tends to infinite, absolute value of an plus 1 divided by an. Right? So root test also, if ratio test fails, then use root test. Root test works, then you conclude whether it is convergent or divergent. If root test also fails, like if it is giving us inconclusive result, then finally we will use the comparison test. We try to compare it with some other very well-known series, and then conclude whether it will converge or diverge. So this is the flowchart that you can follow to solve problems related to series convergent and divergent. On the left hand side, you can see many examples. Let's walk through each of the example real quick. Okay, so if you look at the first series, the first term is half, the second term is 2 by 3, the third term is 3 by 4. Now, if you write down the corresponding sequence from this series, you will have 1 half, 2 by 3, 3 by 4, 4 by 5, and so on. Right? So this will be the sequence. Now, what do you think the limit of the sequence is? So what is the limit of the sequence? Limit n tends to infinite. What is an? An is n minus 1 by n, or n by n plus 1. Right? So an is n by n plus 1. So what do you think will happen to the limit as n tends to infinite? What will happen to n by n plus 1? It will go to 1, which is not equals to 0. Right? The sequence limit is not tending to 0. So straight away, what can we conclude? This series diverges. Right? So you don't have to use any test. You are not using ratio test. We are not using root test. We are not even using comparison test. All we are using is looking at the series sequence convergence and its limit. Basically, that limit is going to 1, which is not 0, and we are directly concluding that this series converges. This series diverges. You look at the second one, which is 1 plus 1 by 1 factorial plus 1 plus 2 factorial and so on. If you write the corresponding sequence, you will have 1, 1 by 1 factorial, 1 by 2 factorial, 1 by 3 factorial, and so on. So I'll take this here. This is for ratio, this is for root. Okay. So now you see this sequence 1 by 1 factorial, 1 by 2 factorial, 1 by 3 factorial, like this. The nth term will be 1 by n minus 1 factorial, right? So as n tends to infinite, what happens to 1 by n minus 1 factorial? So n grows in the denominator, and the denominator will go to infinite. So 1 by infinite will be 0. So the sequence limit is tending to 0. Now we have to use different test, the next test, which is ratio test. You can check the ratio test. Yes, Shudhanshu.
Sir, how that will be equal to 1? Limit n tends to infinity and upon n plus 1.
So you can bring this n to the denominator, no? You divide the numerator by n and denominator by n. Then you will get this expression as 1 by 1 plus 1 by n, right? So the same expression rewritten like this, 1 by 1 plus 1 by n. Okay. Now as n tends to infinite, 1 by n will go to 0. So 1 by 1 plus 0 will be 1.
Okay, sir. Okay. Thank
Okay.
you.
Yeah. So here, the second problem, you can use the ratio test, and you will observe that you see this limit n tends to infinite. We are using the ratio test. Ratio test is like n factorial by n minus 1 factorial, right? So n plus 1th term is, sorry, n plus 1th term is 1 by n factorial. One by n factorial divided by a nth term is 1 by n minus 1 factorial, right? So if you simplify this, n factorial, I hope everybody know it can be rewritten as n into n minus 1 factorial, right? So this and this will get cancelled out, and there will only be n left. And this will give you 1 by n modulus limit n tends to infinite. And you will get L, the limit value as 0. Our capital L is 0. So once the capital L is 0, which is like L is less than 1, so you can, we will claim, we can say that this particular series actually converges, and it will converge to a value which is Euler number E 2.714, which we'll see in some time, within 1 hour. Okay, so this is how we have used ratio test to conclude this particular series actually converges. Now, if you look at the third example is like half plus 1 by 2, like half plus 1 by 4 plus 1 by 4 plus 1 by 8 plus 1 by 4, 1 by 8, and so on. So we have taken this example just to show you that the ratio test will fail, but the root test will pass. Okay. So we will take that later. Let's finish quickly 4, 5, 6. If you see 4 actually 1 plus 1 by root 2 plus 1 by root 3 and so on. You can use the ratio test, and you will see that this will actually converge. Okay. And this is also 1 by n power q series, where q is half. Okay. So that will converge. And even this also, fifth one, you can use ratio test, and it will also converge. Okay. So this will also converge. What about the last one? Even 1 plus 1 by 3 plus 1 by 5 and so on. If you write down the sequence 1, 1 by 3, 1 by 5 and so on, right? So this sequence will tend to 0. And if you write the nth term, it will be 2n plus 1, right? 1 by 2n plus 1. Nth term will be 1 by 2n plus 1 plus n plus 1th term will be 2n plus 3. Now you compute limit n tends to infinite, absolute value of an plus 1 by an. This will be limit n tends to infinite. An plus 1 is 1 by 2n plus 3, and this is 1 by 2n plus 1. An is 1 by 2n plus 1. If you simplify this, you will see that the limit will actually go to 1, which will give us that the root test actually, sorry, ratio test will actually fail, or no conclusive result will obtain. Even if you use the ratio test, sorry, root test, even that will also give us the same result, no conclusive result. So for sixth problem, ratio test will fail, root test will fail. The only thing we can use is the comparison test. So we'll compare this particular series with a well-known series. Okay. So that series is uh, okay. So that series is so we have the odd terms here, 1 by 1 by 3 plus 1 by 5 and so on. And there are no even terms, right? So 1 by 6 plus 1 by 8 plus and so on. So if you pull out, so we know that 1 plus half plus 1 by 3 plus 1 by 4 plus and so on, which is summation 1 by n, actually diverges, right? And we have written the same summation as two different summations, right? So 1 plus 1 by 3 plus 1 by 5 and so on, and plus half plus 1 by 4 plus 1 by 6 plus 1 by 8 and so on. So what we have is, here we have one series which we are looking for the convergence and divergence. If you see the next part, this part, and you pull out half common from this part. If you pull out a half common, you will have 1 plus 1 by 2 plus. Okay. Okay. So what are we going to do? Okay, just give me a minute. Let me think about this. So problem 6 actually, we will use comparison test. Actually, it will diverge. Right now, I am unable to get the proper comparison series. Just hold on. If any one of you have any thoughts, you can just let me know. Okay, you can also help me out. Any thoughts from anybody? Any suggestions? So the thing is, definitely the ratio test and the root test will fail here. So we will be left with no other chance than to use comparison test. But we have to come up with such a series which will diverge and also lesser than each of these terms. Okay, so if smaller series itself diverges, then we will claim that the larger series will diverge. Okay, so maybe you can come up with that series later.
Sir, I wrote the mail, but
Okay, can we discuss this at the end, Mayank, if you don't mind?
option.
Yeah. Oh, it seems like it's converging. Ah, it may seem like that, but it will not converge. Okay, we will discuss this later. Let's discuss problem 3. Okay, so I'll come back to that. Limit will come out to be 0. That we discussed, no? Even though the sequence tends to 0, it necessarily doesn't guarantee that the series will converge. Okay, so let's finish this first. Let's finish problem 3, which is half plus half plus 1 by 4 plus 1 by 4 plus 1 by 8 plus 1 by 8. So like this, if we proceed, we can write down the nth term when n is even, nth term when n is odd also. Okay, so this will go like this, and this will be 2 power n minus 1 by 2, n plus 1 by 2. When n is odd, you can check. So when n is 1, you will get 2 1 by 2 power 1 plus 1 by 2, which is 1 by 2 power 1, which is half. When n is 3, 3 plus 1 by 2, which is 4 by 2, which is 2. So 1 by 2 square will give us 1 by 4. So similarly, when n is 5, n is 6, n is 7, and so on, you will just substitute. You will see that the odd term, when n is odd, you will see. So this is when n is odd. Okay. And when n is even, you can easily write that, which will be 2 power n by 2. Right. So you can check. When n is equals to 2, you will have 1 by 2. When n is equals to 4, you will have 1 by 2 square, which is 1 by 4. So like this. So if I use the ratio test, okay, again, I have to, if I am using the ratio test, again, I have to use it on two cases, when n is even, when n is odd. Okay, so when n is even, okay, so when n is even, you will see that nth term and n plus 1th term will change, right? So when n is even, our an is 1 by 2 power n by 2, whereas an plus 1 is 1 by 2 power 2 power n plus 3 by 2. So n plus 1 plus 1 by 2. N plus 2. N plus 2 or n plus 1 by 2 plus 1. Right? So n plus 3 by 2. So then we can compute L when n tends to infinite, absolute an plus 1 divided by an, which is limit n tends to infinite 1 by 2 power n plus 1 by 2 plus 1 divided by 2 power n by 2. So if we come 1 by 2 power n by 2, if we compute the limit, this will be 2 power n by 2 divided by 2 power n plus 3 by 2. Right? So as n tends to infinite, you can see 2 power n by 2, 2 power. So this will give us 2 power n by 2, 2 power n by 2 will get cancelled out, and you will have 2 power 3 by 2. This is when n is even. Similarly, if we have to do for n odd also. So in both the cases, it should go to the same limit value. Right? So when n is odd, you can see that your an will be 1 by 2 power n plus 1 by 2. Our an plus 1 will be 1 by 2 power n by 2. Right? So these will be our anth term and an plus 1th term. So the same thing. So we'll have half, half. If your an is 1 by 4, your an plus 1 will also be 1 by 4. So if your an is 1 by 8, your an plus 1 will be 1 by 8. So when n is odd, your n plus 1th term is same as nth term. So therefore the limit, yeah, so this will be n plus 1 by 2. So therefore the limit as n tends to infinite, when n is odd case, you will have an plus 1 by an as 1. Because your odd term and the even term is the same. So when you take the ratio or between the same terms, you will get 1. And you can see when n is even and when n is odd, you are getting two different limits. When you get two different limits, then obviously limit does not exist, which says that the ratio test, the limit does not exist. Therefore, we have to use the root test. So if you use the root test, so we have to use a root test. Again, even in the root test also, you have to use different cases. When n is odd and when is even. When n is even, you will see that limit n tends to infinite 1 by 2 power n by 2 whole power 1 by n, which is 1 by 4. Right? So n and n will get cancelled out. Sorry, root 2. Okay, so n and n will get cancelled out. You will have 1 by 2 power half. 2 power half is nothing but square root 2. So you have, when n is even case, you will have 1 by root 2. When n is odd, you can see that limit n tends to infinite 1 by 2 power n plus 1 by 2 whole power 1 by n. Even in this case also, uh, you can see that you will get limit n tends to infinite 1 by 2 power. So 1 by n goes in to the power, it will become n plus 1 by 2n, and limit n tends to infinite. This will be 1 by 2. If you divide, you will have half plus 1 by 2n. Now when n tends to infinite, you will get 1 by, this term will go to 0. So you will have 1 by 2 power half, which is 1 by root 2. So you can see here, when n is even and when n is odd, in both the cases we got 1 by root 2. So that means limit exists and it will be equal to 1 by root 2. So 1 by root 2 is less than 1. So we can claim that by root test, this particular series actually converges. Okay, so by root test, the given series converges. Okay, but the ratio test has failed, which implies that there are series for which the ratio test may not exist or inconclusive, falls into inconclusive case, but root test may exist. Okay, so root test can give you. So here the third example will also converge. Okay, so we'll look it up the sixth problem at the end or maybe in the next session. So the thing is, we have to come up with some other series which is diverging, and that will be compared to this particular series, and we'll claim that this will diverge. Okay, so yeah, so that's about the root test and ratio test. Yes, any doubt? Okay, now let's talk about power series. So far we have talked about series. Now power series is slightly different. It's a series, but there will be an extra term, extra expression in each of the terms, which is x power k. Okay, so you have a sequence of real numbers ak like this, and then for some fixed x, now x is a variable. Okay, x can take any value between minus infinite to plus infinite, and you consider a new sequence like this. ak x bar k. Now if you write down the terms in this sequence, you can see that a naught will be your first term, a1x, a2x square, a3x cube, and so on. And from this sequence, we will write the partial sums. Okay, so you consider another series, another sequence, which is like you generate another sequence from this sequence, where your first term of the new sequence is same as the first term. Your second term will be the sum of the first two terms. Your third term will be the sum of the first three terms, like this. And you can, this particular sequence has infinite terms. So you can get infinite number of terms in this new sequence also. And as n tends to infinite, or you see the last term of this sequence, which is the power series. So as n tends to infinite, you look at Snx. So Snx is the partial sum, okay, which is from the first term to the nth term. You sum up the first term to the nth term and tend n to infinite, which implies that you are adding up all the terms in this sequence. Okay, so that is like summation k is equals to 0 to infinite ak x bar k. And if you see the expression in the expanded version, you can see that it is nothing but a naught plus a1x plus a2x square plus a3x cube plus and so on. So nothing but you are adding up all the terms in this particular sequence, which is called the power series. You would have seen quite a few examples of power series. The very well known power series expansion is this 1 plus x square by 2 factorial plus x cube by 3 factorial plus x power 4 by 4 factorial and so on. So this is a power series. And if you closely observe this power series, this expression, it is like a polynomial, right? So you have the constant term, linear term, quadratic term, cubic term. But what is the change? The change is the degree of this polynomial is infinite, right? So there is no, so the degree of this polynomial is not defined. So it can be 1,000, it can be 1 lakh, it is like infinite. It has x power 1,000 term also, it has x power 1 lakh term also, and it has x power something very large number. So it's like an polynomial with infinite degree. Power series is that. Okay, you can think of it that way also. Okay, so that is power series. And the next thing is, after we learned series, we talked about convergence and divergence of that series. The same thing we will do here. Even the power series, when does the power series converge and when does the power series diverge? Okay, so that's the next thing we are going to do. And these are some more visualizations on power series. So you take this 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. So that is the power series. And you take the nth term, so nth partial sum, which is like you add up n terms together, and you see you take a fixed value for x, let's say x naught, then it will just become 1 plus x naught square by 2 factorial plus and so on x naught power n by n factorial. Now you can plot this by fixing n. So initially you fix n is equals to 1. That means that will be simply 1 plus x. It's a straight line. When n is equals to 3, it will be 1 plus x square by 2 factorial plus x cube by 3 factorial. You plot that. So like that, the right hand side curve actually starts from n is equals to 4, n is equals to 8, n is equals to 16, and x denotes n is equals to 32. So that means you take the first 5 terms, first 9 terms, first 17 terms, first 33 terms. Okay, so if you take and plot, you see that when you take the 4 terms, it will be like this. When you take 8 terms, it is following like this. When you take 16 terms, it is like black line. When you take 32 also, you will start observing that it is almost equal to the black line only. So it is following the same back line path. So if you take 64, if you take 100, then if you take 1,000 also, it is more or less follows this same curve. And x naught can be somewhere here. Okay. So what we are doing is basically we are trying to plot this particular expression. Yes. Yes, Krishna.
Sir, why all the curves are going similarly as x power 16?
Huh. Because this particular series or this particular expression, even though you keep adding the terms, so n is like if you increase n, that is nothing but you are adding more and more terms, right? Even though you add more and more terms, slowly what happens to this expression is this whole expression goes and converges to one single function, which is e power x, which we are going to see in some time. Okay.
Okay, sir. Due to the nth factorial in denominator, I think.
Huh. No, not due
Okay,
to
sir.
that. It is actually
Oh,
saying, proves us that this particular expression will converge as you,
okay.
even though you tend to infinite, this will not blow up or this will not give different expressions or different curves. As you increase n, this whole expression will start behaving like a function. One good function which is e power x, which will be e power x. That we'll see in some time. But it may not happen for any other expression, every other expression. That also we'll see in some time. So this particular expression is actually converging. That's it. Okay. So like this at x naught. So if you fix x naught, you will see that you will compute this 1 plus x naught square by 2 factorial plus and so on. You will see that initially when you take n is equals to 4, your value will come up like this. As you increase n, your value will change and slowly converges to one particular value. Okay, as you keep increasing your n, this 1 plus x naught square by 2 factorial. So now it is independent of x. It is fixed value. X naught is a fixed value like 3, or here it is 4.21 or something. So you take 4.21, it just becomes a series. 1 plus 4.21 plus 4.21 whole square by 2 factorial plus and so on. This particular value, as n tends to infinite, starting from 4, it will take this value, this value, this value, and so on, and it will slowly converge to this point. Similarly, you move this x naught from somewhere 0, minus infinite to plus infinite. So for every x naught, this will go converge to a fixed value. Okay, so like this, you can plot the power series, and if your power series converges, then you will get a nice fancy curve. If your power series diverges, which means if you add more and more terms, if it is going to infinite, the expression will go like this. So starting from here, it will go above, and above. So as n increases, it will not converge, it will diverge. That we'll see. Okay. So here, if you see the geometric series, you see the geometric series, which is 1 plus x square plus x cube plus and so on. So we have this expression, right? If your x is less than 1, then your geometric series will converge. So something like this. So if your x is, let's say, if your x is 0.91. So if your x is 0.91, so it will be like 1 plus 0.91 plus 0.91 whole square plus 0.91 whole cube and so on. This summation will converge to a fixed value, proper value, and that you can see from the plots. So it may start from here, then go here, go 91, right? So it might start from here, will go here, and so on, right? So it will go converge to this value. It will not blow up suddenly. And for every x which is less than 1, you can see it will follow some nice curve, which will be equal to something like 1 by 1, 1 minus x. So this is a function. You observe this 1 by 1 minus x is a function, nice function. The left hand side is a power series, but the right hand side is an expression, function expression, 1 by 1 minus x. And if you plot 1 by 1 minus x, it will look like this, something like this. Okay. Yes. Yes, Abhishek. Abhishek, if you are speaking, you are on mute. Okay. Okay, let me continue. If you want to ask, you can unmute and ask. Okay. Okay, if x is greater than 1, what happens is you can see here. So slowly, when n is equals to 4, n is equals to 16, n is equals to 64, n is equals to 256, you can see that this will blow up like this. And if you further increase, if it is 512 or something, it will go like this. If it is 1024, or if you increase terms, it will go like this, like this. And it will not stop, it will not converge to a fixed function. So it will change, it will keep on changing. And at last, what happens is, even for x is equals to 1, it will start from infinite. So if you take infinite values, when n is infinite, even for x is equals to 1, you will have 1 plus 1 plus 1 plus and so on infinite. So it will be like a flat line at the infinity. Okay. So what this plots and visualization tells us is, the power series is not like series. So if you see series, you can actually conclude series converges or diverges, right? So there is no converging and diverging within the series itself. Whereas coming to the power series, since we have this x coming into the picture, so the convergence and divergence depends on the values of x. So for some values of x, it will converge. For some other values of x, it will diverge. Okay, the same power series. We are not changing the power series here. Okay, so you have to keep that in mind. So that's the difference between series and power series. Series, you can conclude whether it is converging or diverging, or any given series will either be convergent series or divergent series. Whereas power series, depending upon the value of x, it may converge, and some other values of x, it may diverge. The same power series. There is one more example, which is x plus x square by 2 plus x cube by 3 plus and so on. And this also in future you will see that this is nothing but log x. Right? So 1 minus log x, if I have to be more specific, or log 1 minus x. Okay, so we'll see that in future, but as of now, you see that this is also a power series, right? So it is like x plus x square by 2 plus x cube by 3 and so on. If you write it in the summation, so n is equals to 1 to infinite, 1 by n into x bar n, right? an is 1 by n here. Okay, so an is, this is an 1 by n, right? Even this power series also will converge for all values of x which are less than 1, and it will diverge for all values of x greater than or equals to 1. Okay, so for some interval, something like -1 to +1, this will converge, and beyond left of -1 and right of 1, it will diverge. So like that, what I wanted to conclude within these slides is, the power series convergence will depend on the interval of x. So depending upon the value of x, we will conclude whether it will converge or diverge. Okay. So that interval is called the radius of convergence. Okay. So what is radius of convergence of a power series is, so you have a power series with you and you compute. So this is the power series and you have the coefficients an and x bar n. You take the coefficients separately and form a sequence and then compute this limit. So this limit is the root test limit. Okay, so alpha limit. So you compute this limit and let's say it is equals to some alpha. If you get alpha as some 2 or 1.5, then the radius of convergence will be 1 by alpha, which is 1 by 1.5 or 1 by 2. So whatever the limit value you get here, okay. So here observe, This limit value can be greater than 1 or less than 1. Anything will happen. Can be equal to 0, can be infinite. Okay. So you should not conclude just by computing this limit, and don't compare this with root test. Okay. So root test here we are not going to use, because as I said, the same power series can converge and diverge for different values of x. Okay. So what this radius of convergence is you compute this limit, and whatever the limit value you get, you just reciprocate. You just do the 1 by of that limit value, which will give you the radius of convergence. That is the radius of convergence. And if you have the radius of convergence as 1 by alpha, you can see that if alpha is 0, then R is infinite. If alpha is infinite, R is 0. And how do we use this R? We are going to say this particular power series will converge if mod x is less than R. Okay, if mod x is between minus, if x is between minus R to plus R, in that interval, it will converge. If it is less than minus R and greater than plus R, it will diverge. Okay, so this R is called the radius of convergence, and we are going to use this radius of convergence to conclude in which interval our power series will converge and in which interval our power series will diverge. Okay, so you can prove actually you can use the root test, right? Our nth term is an x power n, right? So you can treat this as bn now. So if I am going to use the root test, so then limit n tends to infinite mod bn whole power 1 by n, right? So this should be less than 1 basically for convergence, right? So for convergence, this limit should be less than 1. Now what is bn? Bn is an x power n. So limit n tends to infinite mod an x power xn x power n whole power 1 by n less than 1. And this you can rewrite it as limit n tends to infinite mod an whole power 1 by n. This x power n power 1 by n will simply become x mod x less than 1. And you can take this on the right hand side, you will get mod x less than 1 by limit n tends to infinite mod an whole power 1 by n. So this is nothing but alpha. That is what we have said. That limit is nothing but alpha, and 1 by alpha is nothing but r. So if your mod x is less than that r, then we are going to satisfy this condition, and this condition implies our series will converge. So therefore, mod x less than r, our series will converge. Mod x greater than r, our series will diverge. That's it. As simple as that. Okay. So there are multiple examples. We can solve a couple of them and compute the radius of convergence. So the radius of convergence concept is definitely useful for your quiz too. So there could be questions on this computing radius of convergence. So we can compute the radius of convergence for the first one itself. So 1 plus x square plus and so on. So for this, if you see an is actually, if you write this as summation n is equals to 0 to infinite an x power n. So we have to write it in this form. So if you see carefully, an is 1 because all the coefficients are 1, right? So an is 1 for all n. Therefore, limit n tends to infinite mod an whole power n will simply be, this is alpha, will simply be limit n tends to infinite 1 power 1 by n, which will give 1. So if alpha is 1, then the radius of convergence will be 1 by alpha, which is 1 by 1, which is 1. Therefore, 1 plus x square plus and so on, this power series will converge if mod x is less than r, r is 1, so mod x less than 1, and this will diverge if mod x greater than or equals to r here is 1. Okay, so easy. And if you take this exponential, so summation x power n by n factorial. So here an is n factorial, right? So alpha will be limit n tends to infinite 1 by n factorial whole power 1 by n. So computing this limit is slightly trickier. So let's try to use the ratio, which is 1 by n plus 1 factorial divided by 1 by n factorial, right? So an plus 1 by an. So if you see, this will just simply be n plus 1, and as n tends to infinite, this will become 0. So alpha became 0. So if alpha is 0, our r is 1 by alpha, which is infinite. R infinity tells us that this will converges when mod x is less than infinity. And we all know x is a real number. So if x is a real number, then it will definitely be less than infinite. So what does this say is this particular series always converges. No matter what the x value is, it will always converge. From minus infinite to plus infinite, for any value of x, this will converge. And that is what we define as e power x. So e power x is defined from minus infinite to plus infinite, right? So irrespective of x value. So yeah, so there are power series which will converge for any value of x, and there are power series which will never converge at all. Okay, where when your alpha becomes infinite, your r becomes 0, and it will eventually tell us that it will converge for mod x less than 0. We all know that mod x is a positive quantity which should be always greater than or equals to 0. Mod x less than 0, which obviously imply that no matter which value of x you take, it will always diverge. Okay, so something like n power n x power n. So you see this. So n power n x power n will always diverge. You can check that. You use the same thing. You try to compute alpha, you will see that alpha will be actually infinite. If alpha is infinite, r will be 1 by infinite, which will be 0. It will always diverge. So this particular power series, sixth one, will always diverge. Okay. So any doubt here so far? So far what we have discussed is, we have talked about root test, ratio test, and then we have seen some examples of root ratio test and root test. And some examples also we saw that where ratio test will fail, but root test will help us. And some examples like example 6, both the tests will fail, and comparison, we have to use comparison test. Okay. And then we talked about power series and what exactly power series and its convergence. Is power series convergence will depend on the values of x, right? So in some interval it will converge and in some interval it will diverge. And finally, we talked about the radius of convergence, which is like in which interval it will converge and in which interval it will diverge. Okay, and we also how to compute this radius of convergence using the limits. Okay, so we will take 5-minute break. At 9:15, we will start talking about functions defined using power series and exponential functions also. Yes, any doubts?
Sir, if any expression is convergent for any value of x, like
Hmm.
e to the power x, it
Hmm.
means that expression is representing any function which is
Function.
okay. Or
Yeah.
if that expression is convergent in some interval,
Hmm.
then it is another function which is defined on that only particular function.
Only
Am I right?
interval. Correct. Exactly true. So this 1 plus 1 by
Okay.
x, this 1 plus x square. What is this? Okay. So this 1 plus x square and so on will actually be equal to 1 by 1 minus x only when mod x is less than 1. Okay, so that will also come into the picture. So this will be representing a function only if mod x is less than 1. Okay, so that need to be mentioned. Whereas for e power x, we don't have to mention any interval for x. Okay, all right.
Okay, sir.
So
Thank you.
yeah, yeah. All right. So we'll take a short break. We will resume at 9:15. Okay, at 9:15 we will start talking about the functions. Okay, so how do we represent power series as a function? Okay, and then we'll talk about exponential functions also. Yeah.
Hello. Is my audible? Hello.
All right, so let's continue. Am I audible?
Yes, sir.
Okay.
Hello.
Yes.
Sir, how can we deal with the n tells to infinity? I'm get lot so much time confused when I see the infinity n tends to infinity. Then how can we calculate it?
Okay, so you are asking me how to compute the limits, more or less, right?
Sir,
How to compute the
in
limits.
so many problems in electronics and thinking also, we had infinite
Hmm.
ladder circuit where n
Hmm.
tells to infinity. How can we
Hmm.
calculate the value?
That is why we are learning this limits, right? So limits actually help us to think about what
Sir,
happens as n
yeah,
takes larger and larger values.
okay.
Sorry.
Yeah, and I'm very much consistent in mathematics, so this is the
Hmm.
mystery for me.
Okay. So that is what. So think. Don't think that n is. If you are too confused about n tending to infinity, think of it like n is tending to some
Yes,
100.
sir. Because how can we
Then think
calculate
like
infinity?
think like next think like n is tending to 1000. Then think like n is taking some value 1 lakh. So something like this. And see the expression. What is happening to the expression? So if it is 1 by n, then it is very easy to understand, right? So 1 by 100 is 0.01. 1 by 1000
Yes,
is 0.0001. Something like that, right?
yes, sir.
So as n value increases, what happens to 1 by n? N is taking very, very large numbers in the denominator. This will become
Yeah.
1 by large number will become 0. So the same thing. So you have to think of it in the same way. Even how complicated the expression is, even the expression is like n square plus 3n plus 1 divided by n cube plus 4n n power 4 plus 2n. Something like this. Even you see this kind of expression, you think of like what happens when n is 1. What happens when n is 10? What happens to it when
Yes.
n is 100? What is happening when n is 1000, 10,000, 1 lakh? So like this, what
I
will
just
happen to
put
the
the
extent?
value of n and find the answer.
See what happens to n1. N is equals to 10, n is equals to 100, n is equals to 1000. And then you will see, slowly start seeing that n is equals to 1, you will see that 1 plus 3 plus 1, which is 5, divided by 1 plus 4 plus 2, which is 7. So it is 5 by 7. Whereas n is equals to 10, you will see something like you have n power 4 in the denominator. So when n is 10, the denominator has 1000 in it. 4 into 1000 will be 4000,
Yes.
right? 4000 plus 100, 4100 plus 20, 4120. But in the numerator, if you see, you have only n square. N square 100 plus 30 plus 1, 131. When n is 1, it is 5 by 7. When n is 10, it is 131 by 4120. When n is 100, you see there is n power 4. So 100 power 4 is like 100 and there will be 8 zeros. Very large, right? Whereas in the numerator, the increment will be very less. Now you will start observing that as n increases, your denominator will just blow up like anything because you have n power 4 in the denominator. Whereas
Yes,
you
sir.
have only n square in the numerator. So you have to think in this particular manner. If you are unable to think directly what happens to n tends to infinity, you can start in a stepwise process. Okay. It will take some time, but as you solve more and more problems, the solving will get speeded up, and you will also get to understand what is actually happening. When you see the expression straight away, you will observe something after a
Okay,
certain
sir.
period. Okay. Okay.
Yes.
All right. So I hope this will help to many others also. They didn't ask. That's it. Okay. So let's come back to week 7. And now what we talk about is we will talk about functions defined using this power series. So what do we mean by this? So even though it looks like an sum of infinity terms, sometimes if it is converging, that will converge to a function. So we can represent the power series as a function, some expression, simple expression without any summations involved. Okay, so we'll see that. So this is the power series we have, which is summation a n x power n, and we know that if we can compute the radius of convergence, and we can say that this particular power series will converge when mod x is less than r, right? And we can actually compute the partial sums, and then we see that as k tends to infinite, as k tending to infinite is nothing but you keep on adding terms to this particular summation. Slowly, if your x is less than r, so that means if you are in the radius of convergence, if your x is within the limits, then you will observe that this sk as k tends to infinite will approach to a function. Okay, so for very large k, this sk is approximately equals to fx. Okay, then once you have fx with you, you can actually plot and you can actually comment on its continuity, differentiability, everything, right? So that we can do. We can also invert it, but we will not focus on that too much. That we will use it when we talk about logarithmics. Okay, so there are few examples here. The first one is geometric series that we have discussed just now. So this 1 plus x square, the left side is the power series, whereas the right side is just a function, is an expression 1 by 1 minus x. So you can actually write this whole power series as 1 by 1 minus x only when your mod x is less than 1. Okay, so careful about that. And this is a rational function, right? So 1 by 1 minus x is a rational function. So this geometric series, we have represented it as a rational function 1 by 1 minus x. Once it is a rational function, you can see that it is only discontinuous at x is equals to 1. Every other place it is continuous. And you can also talk about the differentiability. You can take the differentiation because our x is between minus 1 to plus 1. So within this is continuous, right? So once that is continuous, and if you plot it, you will also see that it will be smooth. You can take the differentiation also. So if you take the differentiation, you will see that 1 by 1 minus x is nothing but 1 by 1 minus x whole square. Okay. So I hope most of you know how to take the differentiation of a function. And on the left hand side, if you see, if you take the differentiation of each term, what do you think you will get? 1, right? X square. So if I take the differentiation of 1, okay. So if I take the differentiation of 1, okay, is my
It
voice
will be
clear?
0.
It will be 0. If I take the differentiation of x, it will be 1. If I take differentiation of x square, it will be 2x.
2x.
Similarly, I'll get 3x square, 4x cube, and so on. So this expression 1 plus 2x plus 3x square, and so on. When this expression, when mod x is less than 1, this will converge to 1 by 1 minus x whole square. Okay.
So isn't it minus 1 by 1 minus x square?
Because you see there is minus x here, right? So 1 minus x whole power minus 1. If you take the differentiation, it will be minus 1 into 1 by 1 minus x whole square into the derivative of 1 minus x. So the derivative of 1 minus x will be minus 1. So it will minus 1 and minus 1 will get cancelled out and it will become plus 1.
Okay, sir.
Okay. Yeah. So you try it out. Just use the differentiation rules that you know, you try it out, you'll get this. Okay. So once your power series converges to a function, then you can actually take the derivatives of that functions and talk about convergence of some other functions, some other series. So this 1 plus 2x plus 3x square plus 4x cube and so on, which is nothing but n into x power n minus 1 expression, right? So you can actually say that this particular expression will converge to 1 by 1 minus x whole square when mod x is less than 1. Okay, so again, this x plus x square by 2 plus x cube by 3, this we have seen, x power n by n, right? When mod x is less than 1, this series will converge. And this will converge to some logarithmic expression, which we don't talk about it here now, but we will study this later. Okay, even continuity and derivatives also we will talk. And the last one is the e power x. So the here x belongs to the real given here. So for any value of x, this will converge and this will converge to exponential function e power x. Okay, so like this, our power series can be represented as a function in its radius of convergence interval. Okay, and yeah, the same thing, continuity and differentiability we can talk. If you have a power series like this, and if it is converging for in some interval, in this interval, then f is continuous and differentiable in that interval. And what we can actually write is, you can actually take the derivative of each term separately, and when you take the derivative each term separately, you will get something like this. And into, so you just have to take the derivative. An is constant anyway, constant will stay as constant. X bar n derivative will be n into x bar n minus 1. So each term will now become n into an into x bar n minus 1. The radius of convergence will stay as it is. Okay, so the differentiation of power series can be done term by term. That's it. Okay, so you can do this repetitively. So this is the first derivative. If you take the second derivative, you take the derivative of the derivative. So then it will become n into n minus 1 into an into x power n minus 2. Like that, if you take the kth derivative, now the nth term will look like this, n into n minus 1 into and so on, n minus k plus 1 into an x power n minus k. Okay, so you have taken k times derivative. So you'll have k terms here, right? So this will be the example. This will be the expression. So here are the examples again. So the same example, you see 1 plus x square and so on is 1 by x, we know, when mod x is less than 1. And if you take the derivative on the left hand side, it will become 1. So this will become 0, this will become 1, this will become 2x, x cube will become 3x square, and so on. So this will be the derivative of this expression, which is 1 by 1 minus x whole square, and the radius of convergence stays the same. If you further take the derivative once again, you will have something like this. So 1 becomes 0, so 2x becomes 1 into 2, 3x square will become 3 into 2 into x, which is 2 into 3 into x, plus 3 into 4 into x square, and so on. And if you further take one more derivative, so the derivative of, so I will do this derivative, the derivative of 1 by 1 minus x whole square by dx is nothing but derivative of 1 minus x whole power minus 2 d by dx. Right, so this is a composition of two terms. So one is x power minus 2 and another one is inside 1 minus x. So if I take the derivative of x power minus 2, it will be minus 2 into x power minus 3. So x here is 1 minus x, and I have to take the derivative of 1 minus x. So this will be minus 2, 1 minus x whole power minus 3 into 1 minus x derivative will be minus 1. Right, so it will just become 2 by 1 minus x whole cube, which is 2 by 1 minus x whole cube. Again, mod x should be less than 1. And you can take derivatives again and again and again. You will get new power series and their corresponding function representation. The second example is the e power x example. So exponential of x is summation n is equals to 0 to infinite x power n by n factorial, which is this, and this will be e power x or exponential of x. If you take the derivative, e power x derivative is exponential derivative of x, and on the right hand side you will see that if you take the derivative of 1 it will be 0. If you take the derivative of x it will be 1 1. If you take the derivative of x square it will be 2 times x divided by 2, that and this will get cancelled out and you will get x. If you take derivative of this you will get this term. So like that, if you take the derivative of the whole power series you will get the same power series again, same x power n by n factorial again, which is nothing but exponential of x, right? So exponential derivative will be exponential of x, and if you take the second derivative you will see that you will again get the same exponential of x. Like that, even though you take some k derivatives you will get the same exponential of x. So what does it says eventually is e power x and its slopes at each and every point, if you plot them it will again give you e power x. Okay, so such a nice function, right? So that's about e power x. Even this logarithmics you can compute you can take the derivative and you will see that you will get 1 plus x square and so on, which is a geometric series, and it will just be 1 by 1 minus x. So the antiderivative will give you ln 1 minus x, logarithmic of 1 minus x. So that we will study later. Okay, so this is about power series represented as functions, and those are represented as functions only. Careful, we just have to be careful about the radius of convergence. Okay, so the next thing we will study is the exponentials. I hope most of you know these exponential functions. So exponential of x is denoted as 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. So the first property which we have seen just now is no matter how many derivatives you take, you will get the same expression. And e power x, e power 0. So if your x is 0, you will see that every term after 1 will become 0 and you will get 1. So e power 0 is 1. And when x is 1, when x is 1, you will have 1 plus 1 by 2 factorial plus 1 by 3 factorial and so on. So that is defined as Euler number, which is e. Okay, so exponential of 1 is defined as e, and e is basically equals to or approximately 2.7142 and so on, right? So that is e, and there are few more properties of exponential functions. So exponential of x plus y can be written as exponential of x into exponential of y, and proof is given here. You can go through the proof or the lecture. Okay, so this property is also important. And exponential of x is always greater than 0, right? And exponential of x uh, tends to infinite as x tends to infinite, and exponential is an increasing function, right? If you have seen the plot of exponential, it will look like this. So as x tends to minus infinite, this will go to 0. As x tends to plus infinite, this will go to plus infinite, and it will be very very smooth. So if you choose any 2 points on x plane and a and b, so e power a will, if a is less than b, e power a will be less than e power b, which says that it's an increasing function, nice function. Okay, and e power x multiplied with e power minus x will give you e power 0, which is 1. Okay, so e power minus x will be the inverse of e power x, and e power minus x will look like this. Okay, and e power minus x is also always greater than 0. E power minus x is a decreasing function. Okay, and e power minus x, as x tends to infinite, this will go to 0. Okay, so you can see this is e power x or exponential of x, and this is exponential of minus x. Okay, so both of them will lie above x-axis only. It will never touch x-axis, nor it will go below x-axis. Okay, so these are the plots, exponential of x versus x, and inverse is what we were discussing. Inverse is the logarithmic function. Okay, so we will see that. Now a little more about the number e. Okay, 2.7182 something. Okay, so e is basically exponential of 1, which is 1 plus 1 plus 1 by 2 factorial plus 1 by 3 factorial plus and so on. So 0 factorial is represented to be or is equals to 1, and this also has a very nice proof, very easy proof actually, and you can go look up at YouTube or somewhere, but very nice. So n factorial, you know what n factorial is, and to get n minus 1 factorial, what we do is we divide it by n, right? So using this, n factorial divided by n is n minus 1 factorial. So you just substitute 1 in that. So 1 factorial divided by 1 is 0 factorial. Okay. So, so very nice. 0 factorial is actually 1. It will not be 0. Okay. So this is called Euler's number or Euler's constant. And E definitely is a irrational number. So you cannot represent it using as a ratio of two integers. Okay. So yeah, that's about E. And yeah, even in this slide also, it's mostly talks about exp of n actually nothing but e power n. So that's the proof. So what is the connection between exponential of x and e? So exponential of x is like this and e is like this. So exponential of n when n integer, you can write it as exponential of x1, the sum, if you just put 1, n as 1 plus 1 plus 1 and so on, you can write it as e exponential of 1 into exponential of 1 into exponential of 1 into exponential of 1 n times. So everything will be e. So exponential of n is nothing but e power n, right? So finally, what we conclude is this will hold for when n is integer. This will hold when n is rational, and when if you take, even though you take x to be a real number, exponential of x comes out to be e power x. Okay, so that is what it is, and e power x is the graph. This graph I have drawn. E power minus x also I have drawn. Right, so e power x is a continuous and differentiable everywhere. E power minus x is also the same. E power minus x, you can write it as 1 by e whole power x, and if you expand it as a power series, you will see that it will be 1 minus x plus x square by 2 factorial minus x cube by 3 factorial and so on. Okay, and every property will follow. So e power x plus y is nothing but e power x into e power y, and e power x tends to infinite as x tends to infinite, and e power minus x tends to 0 as x tends to infinite. And similarly, e power x tends to 0 as x tends to minus infinite. E power minus x tends to infinite as x tends to minus infinite. Okay, so you can see it from this graph. And the most important property here, I think you will learn new is when you compare the exponential with the polynomials, exponentials will always beat the polynomials, no matter which polynomial you choose. So even you choose the 100-degree polynomial or 1000-degree polynomial or the largest number polynomial you can ever think of, even with that, e power x will always beat the polynomials. So what will happen is if you take x power n, divided by e power x. As x goes to infinite, this will dominate this, and when denominator goes to infinite, the whole thing will come to 0. Okay, even though you have x power 10,000 or x power very large number, as x tends to infinite, e power x will always dominate. Okay, and the limit will actually become 0 for every n. This is very important for every n. Okay, and proof also you can go through. It's one line proof. Okay, but this property is really important, and we will use it to solve problems related to the limits, certain limits. Okay, so there are bunch of problems. I'll not focus on most of the things. Let's focus on the last two problems, which are slightly trickier. Okay, so the other problems mostly professor has discussed in the lecture. Go through the problems. Okay, so let's solve the last two. Let's take the first one. Okay, so proving e power x is greater than or equals to 1 plus x. Okay, so as we all know, e power x is 1 plus uh, x plus x square by 2 factorial plus x cube by 3 factorial and so on, right? And this is always greater than 0 for all x, right? And you can clearly see that the first two term, the last term will add up some value, it will not reduce, right? So from there you can easily see that e power x is larger than 1 plus x, right? So it will only be equal when x is equal to 0. Even if you plot, you will see that 1 plus x will just touch, and it will just touch here, and it will always stay below e power x. And you can also prove it taking when x greater than 0, when x less than 0. You can think of different ways. When x greater than 0, straight away this is positive. When x less than 0, you will see that e power x will have, when x less than 0, you say some minus alpha. When x is minus alpha, you will have 1 minus alpha plus alpha square by 2 factorial minus alpha cube by 3 factorial and so on, right? Again, even this also, you will start observing that you compare term by term, the whole negative terms will always be lesser than the previous positive term. Okay, so in that way also you can prove, or if you just right away plot it, it will be very easier for you to see that e power x will be greater than or equals to 1 plus x for all x. And now using this, we have to find some lower bound to this expression. Okay, so we know e power x is greater than or equals to 1 plus x. That means 1 plus x is lesser than or equals to e power x. Right? I'm writing the same expression, writing 1 plus x on the left hand side, e power x on the right hand side. Now put x is equals to k by 365. If you put that, what will you get? You'll get 1 plus k by 365 on the left hand side, and on the right hand side we'll have e power k by 365. Now like this, we have to take the product running from, so this pi is like product of the terms when k starts from 1 to 23. Okay, so if you take the product, or if you just take k is equals to 1, okay, it will be 1 by 1 plus 365 lesser than or equals to e power 1 by 365. When you take k is equals to 2, k is equals to 2, this will be 1 by 2 by 365, lesser than or equals to e power 2 by 365, and so on like this. K is equals to 23, we will have 1 plus 23 by 365, lesser than or equals to e power 23 by 365. So now what you have to do is, all the terms are positive. So the here left hand side is positive, right hand side is positive. Here also positive, positive. Everything is positive values. So what we need is, we need the product of all these 23 terms. So what we do is, we take the product of all these 23 terms and keep it on the left hand side, which will be pi k is equals to 1 to 23, 1 plus k by 365 is lesser than or equals to product of the right hand sides. Right, so this will be e power 1 by 365 into e power 2 by 365 into and so on e power 23 by 365. Right, use the properties of exponentials. So e power x into e power y into e power z into and so on, you can write it as e power x plus y plus z and so on. Right, so if you use that property, you will have e power, the power will be 1 by 365 plus 2 by 365 plus and so on 23 by 365. Now this will be equals to e power 1 plus 2 plus and so on 23 divided by 365. So you just have to add the first 23 natural numbers, and you just use the formula n into n plus 1 by 2, 23 into 24 by 2 into 365. Right, so this will be 23 times 12, so 230 plus 46, 256. So e power 256 divided by 365, and this is lesser than or equals to this product. So instead of you computing this product, what we do is we bound it. We bound it saying this particular product will be lesser than or equals to e power 256 by 365, using the property that e power x is greater than or equals to 1 by greater than or equals to 1 plus x. Is this okay?
Yes, sir.
Right. So similarly, you can also show that e power minus x will be always greater than or equals to 1 minus x. If you plot it, you will see that e power minus x will be like this, whereas 1 minus x will actually touch at 0, and it will always stay below e power minus x. And again, the same approach you follow just like part A. What you do is, instead of 1 minus, so instead of x, you substitute k by 365 here. Okay, and you run from k is equals to 1 to 23, you will get an upper bound now. So here this is a lower bound, this is a upper bound, right? So it should be an upper bound. So this is an upper bound. I think professor also corrected this in the lectures, I guess. You take it, you take a look at the lecture. So this is an upper bound. So this will never be greater than or equals to greater than this particular value. Okay, so which actually says that this acts like an upper bound to this expression. Okay, similarly you will get a lower bound for this expression. Okay, so yeah, so this thing you just substitute in place of x, you just substitute k by 365, and write for k is equals to 1, k is equals to 2 and so on till 23, and you take the product, and you will see that you will get a nice good expression on the left side. So this e power, it will get added up, and finally you will get some real number just like this. Okay, yeah, all right. So yeah, I think one thing left from my side, which is commenting on continuity, sorry, convergence for this particular expression. Uh, yeah, so that is, we can actually say this will diverge by comparing this with this expression, half plus 1 by 4 plus 1 by 6 plus 1 by 8 plus and so on. How can I compare it with that? So if you see each term, this is greater than 1 is greater than half, 1 by 3 is greater than 1 by 4, 1 by 5 is greater than 1 by 6. So like this 1 by 7 will be greater than 1 by 8. So every term here, every term, our sequence an is greater than the obtained sequence Cn, right? So if I just prove Cn actually diverges, then I can say An diverges using the comparison test. How can I prove Cn diverges? If I pull out half common from this particular expression, I will have 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus and so on. And this is an harmonic series. And this will diverge. Right? So this we have seen. Harmonic series will diverge. So half of that will not change anything. So half of infinite is infinite. So therefore this will also diverge. Cn will also diverge. So we got a divergent series where each of the term is lesser than our series expression, series terms. So therefore using comparison test we can prove that 1 plus 1 by 3 plus 1 by 5 plus 1 by 7 will also diverge. Okay. So problem 6 actually uses comparison test. Problem 5 you can use ratio test. Problem 4 also ratio test. Problem 3 you cannot use ratio test, you can only use root test. And problem 1 straight away from the limit itself we can decide. Okay, so I hope whatever I discussed I am clear about that. So now you have ample amount of time to submit your week 7 graded assignment. On Tuesday we will solve some 4-5 problems related to graded assignment. So people who are unable to do graded assignment are requested to join that session and clear your doubts. So in that session also you'll try to solve one of the quiz 1 question. So I have solved it. So the answer was correct. So the thing is you have to slightly be careful and solve it. Okay. So that we will do. All right then. Any doubts? Any other doubts? Anybody? So I saw some doubts related to week 6. Are they present here? So Aditya, are you here? Aditya Samantha? Okay, all right. So he's not here. So I think we have all. Oh, you are here. Huh? Okay. Okay, okay. So I'll stop the streaming now and I will solve GA6 question 8 and 9. I think the solutions are also given, but let me solve it. Okay. For others, I think you can leave the session. Thanks all for joining.
Thanks, sir.
Yeah.